welcome to the IONS podcast. Today with me, I have a very special guest. His expertise is extremely timely, given what's happened in the news around batteries and battery safety. So, Matt Paiss, welcome to the pod. Would love to hear a little bit about your background. Introduce yourself, please, and what your current role is, and we'll take it from there.
Well, thanks, Cam. I appreciate the invitation. I am a technical advisor with Pacific Northwest National Labs, and I am here in a personal role representing my perspectives and experience. But PNNL is one of the 17 DOE national labs located in Richland, Washington. And the group that I work in is the Battery Materials and Systems Group. And we focus on a lot of materials development. My focus is primarily around system safety. And so I work on a lot of codes and standards, a lot of education and outreach of what these codes and standards mean, the direction that they're heading, and just to help the industry understand what might be coming down in revisions to codes. But in general, my focus really is the safety of systems that are getting deployed.
Right. So how did you get into battery safety? So would be great to kind of walk us through your career journey, because I think it's pretty interesting. You were a fire chief. No.
Fire captain.
Fire captain.
Yes.
In my mind, that's a chief, personally, just so you know. At San Jose Fire Department.
That's right.
And you've had a career in renewable energy for a long time. So how did you end up in battery safety?
So I think the time that I spent in emergency services, I spent 23 years with San Jose Fire, gave me a very, very strong appreciation for the risks when things went bad, and the need to focus on protecting the built environment, the natural environment, as well as personal safety as technology develops. And so that time that I spent as a firefighter, I also, as you mentioned, I had a background in renewable technology. I studied that in school and had a company that I did training, code development for as kind of my side job. A lot of firefighters have side hustles. And so for me, it was teaching and training and right. Code work.
Right.
And so when I retired from the fire service, I thought I would just continue doing consulting, and the opportunity to work for the lab came up. And I thought it was an excellent opportunity to represent an independent, neutral position rather than working for a specific manufacturer. And I think that the voice of the national labs in this space was lacking. There's a lot of focus on fundamental research and technology development, but when it comes to really trying to answer some of the real questions around safety, there wasn't a lot of guidance from the national lab system. So that was an opportunity to help develop that with PNNL, and they were very eager and supportive to support areas that we saw there being gaps, whether it be helping new codes or products that needed to be supported. And so that's kind of been the focus.
Yeah, no, I think it's highly needed to have kind of that overarching view, really from a national perspective on what does it mean? What does safety mean in the context of batteries, from smaller to EVs to now very large scale grid storage batteries. And, I want to get into, how the concept of safety has evolved over time. We'll get to that. What does that mean from a code perspective? But why don't we start with something that's been in the news, and it's a very vivid example of why this is important. And of course, I'm talking about, the incident, in quotes, that happened at Moss Landing, and it's not the first time either.
That's
and I remember meeting you for the first time at an event in Stanford, and the thing that really stuck in my mind was your comment that, a lot of people have said, well, it was just a serious event, but nobody got hurt, so okay. But the fact is that it created the conditions and the environmental aspect of it and the fallout of materials across a very wide range of population centers, that will have far-reaching safety consequences. And so it is absolutely a very serious event, and we should consider it as such. So from your perspective, and I know you lived down there, right? Could you tell us what happened at Moss Landing? What was the history? What actually happened? And then, where do we think we're going from a regulatory perspective, both in California and nationally, as, these sorts of incidents continue to happen?
Sure. So there's a lot that I can talk about on this. One thing that I can't talk about because I don't know is what actually caused this last fire.
Right.
Okay. So I won't be speaking to that. I won't be guessing.
Yep.
But I think it's really valuable to take a holistic look at that site because it has had 3 fires. And this is just on the Vistra side. Moss Landing encompasses both PG&E property as well as Vistra Energy. And there are batteries on both of those sites. That site as a whole it's number 2 largest battery installation in the world. Well, it was number 1 for a very long time. But on the Vistra side, the design that they chose early on in 2019 was obviously in hindsight considered with a lot of risks. I was able to be involved prior to Fluence building that particular project. I was involved in one of the other bidders on it in my role as a private consultant. And so I was very familiar with that site. And that building, 900 feet long, 3 stories, about 60 feet wide, was a very challenging location to put batteries because the goal was to essentially put as much density as they can in there. So the selection of the battery racks, even down to the cell selection, very high energy dense pouch cell, very difficult to limit propagation. Mm-hmm.
And for listeners who might not be super familiar with the way that grid scale storage is typically installed, is that normal to put it in a big building, or what would you say about
No, it's definitely not normal. However, back then there were not very many large systems. Somebody putting in, 100 megawatt project, there was only a couple that have been done, and so this one jumped right up to 300 megawatts.
And when was that?
So it was commissioned in 2020. So installed 2019, designed 2018. And when you look at the codes that were in place back then, they really didn't address, these kinds of designs. There were not a lot of best practices learned through failures.
Right.
It's important for everyone to understand that codes are reactionary.
Yep.
They're there once we realize that there's a problem, and this is the recommended practice or mandatory practice. So they don't lag behind technology because they're not fast enough. They lag behind technology because they have to respond to a problem. Okay. So
it's also interesting, this really puts the whole industry in perspective. So this was the largest battery installation in the world.
Correct.
In 2018-ish.
When it was designed, yes.
And it was 300 megawatt hours, right?
300 megawatts.
Megawatts, okay.
1.2 gigawatt hours.
1.2 gigawatt
Yeah,
hours.
4-hour battery.
Okay. Which was substantially bigger than anything that had been deployed.
That's correct. That's correct.
Nowadays, I would say that's maybe an average site, right?
Yep.
And big sites are 2, 3, 4 times that.
Yep.
So it's pretty interesting to realize, because those of us who are in the battery space, we've been talking about grid scale storage forever, but it's shocking to realize that it was barely even a thing 6, 7 years ago.
Yep.
And so the growth of the industry, the growth of our understanding about safety, how the codes have developed, it's just really early days still.
And I think that's a difficult, or I guess I should say it's a challenging statement to say that, well, Moss Landing doesn't represent other systems. It's 5 years old.
Yep.
I think the public hears that and says, well, so that this battery installed down the street 4 years ago.
It's only 5 days old.
is that dangerous too?
Yeah.
So
right.
I think that the Moss Landing battery designs need to be held fairly uniquely because they were not a listed system in the sense that, and this is a really important part to talk about when it comes to the listing, and that's UL 9540. To achieve a product certification, it includes the design of the product at the factory lookbacks, quality control, and it's essentially a certification that's given to a product that rolls out the back door. Some of these earlier systems were bespoke, one of a kind, designed on site, and then a different kind of evaluation process was applied, which is called a field evaluation. And this is something that's kind of new to the industry, is the difference between a field evaluation versus the product certification. And the problem with the field evaluation is the quality of that field evaluation, it is not standardized. The nationally recognized testing body that is going out to do that evaluation could be looking at things completely different than another NERDL that goes out. And I have examples of that. I have one project where the NERDL did a very good job looking at everything. Another one where it was actually shocking how little was looked at. And they both applied field labels to these systems. So that...
How many systems do you think get field labeled now?
It's becoming more and more rare because most projects are based on a certified product.
And that's a trend in the industry from a product perspective too. I would say that our perspective on that is that early days people were doing projects. They were one of a kind, putting batteries in containers, sort of building the installation on site, particularly in big outdoor sites. And then over time, we've seen the product companies try to productize that process more and more and have more and more of the integration happening in the factory where it's better controlled.
Yep. So I think all of this goes to the fact that Moss Landing is very unique because of the it was a one-off design. Now, there are a couple of other indoor systems still in California that present some similar risks. Anytime you install a high-energy dense chemistry that's capable of thermal runaway inside a building, you're now triggering, based on the building code and fire code, the requirement for building protections, sprinklers. And what we've seen with water is that it has not only caused failures of energy storage systems due to leaking, water ingress, but on incidents where there was actually a failure of a battery, the overhead sprinklers have made the event much longer, did a lot more damage to other systems. So water, I call water a double-edged sword. On one hand, it's great at absorbing heat. On the other hand, it's conductive, and it can do more damage. And that's what we saw in the first two incidents at Moss Landing. They were not necessarily battery cell failures. In the first one, it was actually due to leaks in the water suppression system. And so there was smoke that was picked up because of a failure in the air handling system. A bearing failed, injected smoke in the building. The smoke detectors detected the smoke, charged the sprinkler system, and there were massive leaks and loose fittings. So the commissioning of the water system was not done accurately. And so that water leak spread, water spread everywhere and caused a lot more damage. And that same kind of failure, similar failure, happened in the Moss 100 building right next door. So
the irony of the fire suppression system causing the fire.
Exactly. Yeah. And this is a point that, the cell is not always the villain. Sometimes it's the victim.
Yes.
All right. I'm going to attribute that to Christina Francis from Tesla. She always says that like that.
That's a great turn of phrase. Well, what do you think the statistics say now? Because I know there's been some debate in the industry. EPRI has a database of incomplete database of incidents that have occurred with batteries, particularly in the field. And it seems like the jury might still be out. But what do you think is where are we today and where were we 5-10 years ago in terms of what is causing a safety incident around a BESS installation?
So, the EPRI report that you mentioned, we helped them write a kind of a deep dive assessment with Twice Analytics on looking at the data from their database. Now, their database is sourced solely by media announced events.
Good.
So it's already, not casting a wide enough net because manufacturers are not anonymously submitting failures. But from the number of incidents that they have in there, somewhere around 60 or 70 incidents worldwide, we saw a spike of failures in the 2019 to 2021 timeframe, primarily due to systems installed in South Korea that were not required to meet a UL 9540. And so there was a lot of integration issues. Water played a role in a lot of those, poor HVAC, poor BMS design. So there was a lot of areas of failure that have been addressed. And so what we're seeing is far fewer failures. And when you compare that to the number of systems being installed, it's significantly less. I think they saw over a 90% reduction in failures. And so I think that is a clear indication that we're doing something right in the product safety standards and the installation best practices.
What do you say to the average neighborhood resident who's faced with let's say a battery installation going into the community? Would you live next to a big battery system?
So I'm glad you brought up the community perspective, and I want to take just a quick step back. And the earlier, I think maybe at the Stanford event, that comment that nobody was hurt. I don't know if you remember, my rebuttal to that was that's not true.
Exactly.
People were hurt, and I don't think that is being given enough respect. That the impact that it had on hundreds of people in that area. I did not personally experience any symptoms. I live about 17 miles north. I watched it from my house burn. But there were people that were in the plume that night, the next day, and even burned a month later, that did have symptoms. So that's really important to acknowledge. And I think that is a really important event that is going to impede the acceptance in the communities. So as long as we have technologies that can produce toxic emissions when they fail, it's going to be challenging in the public light to accept that. So there's really a need to address the safety risk.
And so you're bringing up an interesting point, which is it's more than just fire safety. It's the chemical emissions that would happen in a thermal event, and that's as important to think about as the thermal runaway, which from a battery engineering perspective, usually the perspective is around fire safety.
Yeah, and so you don't necessarily have to have visible flame in a thermal runaway, and so it might not be a flaming event. Sometimes you could say the flames are better because they're consuming a lot of the flammable gases, could be reacting some of the toxic chemicals. A really important point, too, is that the Moss Landing incident was a massive system, 300 megawatts, all essentially, in the same space. And so one of the things that I say to community members is that systems designed today are based on, for the most part, a 20-foot ISO enclosure, rough size. And that what we're seeing in those systems that are deployed where there is a failure is that it's being contained to that enclosure of origin. So the risk is now, what is the risk of a single enclosure? A lot of times community members that are pushing back against a project will say, they'll point to the APS incident in Arizona in 2019 where that exploded. And they'll say, well, if that one was, 2 megawatt hours and it exploded, then what's the explosive force of a 200 megawatt project? And so we have to educate them that failures don't all happen at once. A car fire on the freeway does not extend to every single car in the freeway.
Right.
So that size and separation factor that's in the codes is really proving to be a valuable guidepost in design.
Let's take a step backwards here for a second. So let's get more into the theory of what does safety mean in the context of batteries. Can you walk us through how we as a community should be thinking about safety? Kind of from materials cell level through modules, through systems, and then how we deploy those into the world, what we do to monitor them, what do we do if there is an incident in terms of first responders, et cetera. Can you kind of give us the broader perspective on safety?
Yeah, so let me actually use the word risk for a moment. When you talk about risk, there's an X and Y axis. One is the frequency of failures or frequency of event, and the other one is the consequence of that event.
Yeah.
So if you had a battery, for example, that failed frequently but did not put out flammable gases, toxic gases, and that would not be considered a high-risk event. On the opposite side, one that didn't fail very much, but it was really produced a lot of toxic emissions, that would be considered high risk. Okay, so when we talk about
3 Mile Island,
exactly, yes, correct.
Fukushima.
And people talk about Moss Landing being the 3 Mile Island of this industry. It's more the Hindenburg of this industry. It was really kind of a one-off kind of beast, so to speak. Now, when we talk about safety, it is a systems approach. There are so many different components that need to operate in harmony for the life of the ESS to be considered safe. And that's really critical. It's not dependent on the cell chemistry by itself. It's not dependent on the manufacturer or even the cell failure. Yeah. A lot of the failures that have occurred that are listed in the EPRI database are due to integration, poor integration of the components, poor manufacturing or workmanship, water ingress, poor thermal management, more so than potentially single cell failures. And so that, talking about safety, it's really the holistic system of its design, installation, and operation are part of that safety.
So walk us through how those things add up to, an overall risk assessment of a system. Propagation. Let's get nerdy on battery safety topics here.
So let me introduce a new term, hazard mitigation analysis, HMA. Right. Yeah. That is required in NFPA 855, which is the standard for stationary energy storage. And that's typically performed by a fire protection engineer. And what they do is they look at the potential failure of key components, what that failure would mean, and then what the manufacturer has done to mitigate that design. And so a well written HMA is really going to dive into, for example, what if the BMS charge control circuit fails? What are the fallbacks to prevent a cell from overcharging or over discharging? If there is a thermal runaway of a cell, what is inside the system to ensure that it doesn't explode or propagate to other cells or modules? So, those are the steps that manufacturers really should look at. Is not, for example, an integrator might buy the racks from another manufacturer. So they don't have any control in the design of that cell or that module, but they're integrating it. And that is challenging because they're putting all of their trust in that cell and module manufacturer to have put in the propagations in there. And sometimes they're designed well, others they're not. So that the final integrator is responsible. They're the ones that have to get the product listing, that have to provide the bankability and the backstop for it. And they've got to make sure that safety follows all the way down to the cell design.
What is happening in terms of the code? Is Moss Landing have an effect here in terms of both the technical codes as well as kind of the law around batteries? Where do you see that going?
So let's talk about code first. So NFPA 855 is updated on a 3-year cycle. The code that's out there now is the 2023 edition. The 2026 edition is just about done. It will essentially, at the NFPA conference in June, is where there will be floor votes on any last motions. And barring the results of that, it should be released on the street in fall of 2025. So that's done. That happened long before Moss Landing. So there's no impact from Moss Landing on what the 2026 NFPA 855 is going to be. Now, there's always the ability to get an emergency amendment in there if there's something that we really identified was key. And some have talked about, is it a bad idea to put lithium-ion energy storage inside buildings?
Mm-hmm.
And some might look at that incident and say, yeah, that was not a good idea. But I would caution people to look at, there are many uses of batteries inside buildings, and where do you draw that line?
Mm-hmm. I was going to ask that.
Yeah. So one of the things that we have to balance in
Leave your cell phone at the door?
Exactly. Yeah. How many cell phones?
On the other hand, how many incidents do we see of, e-bikes and scooters and things like that, causing real problems?
That's the number one area of safety concern, is the micromobility.
Mm. And why do you think that is?
Because those, those products do not have to be certified. Now, there was just a bill that passed that's going to require the CPSC to ensure that micromobility devices, e-bikes, meet the product safety standards. So that was a really important step.
Is that national?
It is national, or will be national. But again, when people can buy online from various sources, it's really difficult to enforce that. So that's one, that the products could be, poorly manufactured. The other thing is that they are typically handled very roughly, right? And thirdly, people will try, there's a lot of self-repair that happens in those spaces, especially gig workers that are using their bikes to deliver food or products. If they have a $800 battery that's now lost half its life, they're going to take it to the store down the street to try and get a couple cells replaced, BMS changed. So that repair aspect is introducing a lot of failure mechanisms into them. And then I'd say the fourth part of it is that a lot of these are kept inside people's homes or charged in their homes. And so failures that occurred during that phase are right next to where people are trying to get out of the house.
In your experience as a firefighter, I don't know how to ask this question, but what the percentage of fires that you had to deal with in the real world at a home, how many of those are related to lithium-ion batteries?
So in my career, it was a fairly small number. Most of the fires that are occurring inside residences are cooking fires.
That makes sense.
Yeah. Electrical fires did happen, and I've been to a number of power tools and e-bikes that have caught fire. But it was, when I retired in 2019, it was still on the lower number. FDNY has said that the number of fires that have been caused by lithium-ion batteries have been an 80% increase in their responses. So it's really significant in dense urban settings that have a lot of mobility devices.
Well, I guess it must be inverse correlation between the number of DoorDash deliveries and the number of cooking fires, right?
Yeah, that's true.
all those DoorDashers on e-bikes coming in causing fires.
They're bringing food from certified kitchens.
Yeah.
But so I think there is a holy grail opportunity for a cell that has the power and capacity for micromobility devices. So as a manufacturer, if that's a space that you guys could work in.
Yeah. Well, it's always the inverse correlation to energy density.
Yep.
Right.
Absolutely.
So, one of the things I think that is just inherently more stable about some of these chemistries like sodium ion, which is of course close to our hearts here at Peak, is that it's a highly stable chemistry, but the inverse of that is that it has lower energy density than lithium ion, and so there's always the trade-off within the application.
Yep.
Yeah. Let's see, a couple of other questions here. You had mentioned earlier in an earlier conversation that there was, getting back to kind of the Moss Landing consequences, that there were some California state laws that were being contemplated around the location of battery storage. Can you enlighten us on what's happening there on the legislative front? Yeah,
so the one that I think is of most interest is AB 303, presented by Representative Addis, who is out of Monterey. And that one addresses utility scale systems, so over 200 megawatts. And one of the really notable requirements in it is the siting of the battery. There's a language in that bill that states that it has to be 3,200 feet away from sensitive receptors. And they describe what the sensitive receptors are, and they're like schools and daycares and freeways, environmentally sensitive areas, seismically sensitive areas. And so I think when you look at the unique, makeup of California, it's going to have a very significant impact on the locations for these large utility scale installations. And I don't know where the 3,200 feet came from. Many of the residents in that area might say, well, I live 8 miles from Moss Landing, and, I had rashes and nosebleeds. So now, again, Moss Landing, 300 megawatts burning at once, very unique. If the trend continues, that's just in, single containers, much, much smaller events. And so, but I think that still leaves the gap open for smaller systems. The big concern in dense urban areas, like Manhattan, is a single enclosure that is, 20 to 30 feet away from another building could potentially represent some risk. So I think there's a real opportunity for technologies with lower failure risks for the dense urban settings.
So let's turn this around to a business question. And we've struggled with this. I struggled with this at a previous company, and that is how to actually generate value from "quote unquote" better safety in a battery system. And it's really hard to get a customer to pay you more than the lowest bidder because of perceived better safety. How should the industry think about creating real tangible value out of for lack of a better term, a lower risk product, and really monetize that with kind of hard economic credits?
So what comes to mind is who was the CEO of GM that made that very famous comment around seatbelts? Seatbelts won't sell any more cars. Right. Yeah. And so I think that we have to look back in history to see how things that we take for granted today, seatbelts, airbags, anti-lock brakes, would have been considered inconceivable for a Model T Ford, but would equally be considered inconceivable in a vehicle that we would buy today to not have any of those. Mm-hmm. Okay. Mm-hmm. So I think that at the early stages of making safety a standardized component of a product, we really need to understand it needs to show its effectiveness, first of all. And so the challenge that we have in the energy storage space is that we still have a very energetic cell that to have a same amount of energy density in a technology that does not go into thermal runaway, produce flammable gases, that's still the barrier. So what kind of safety protections can we put around it to limit the risk to the public? And so that's what you're talking about. That's the seatbelt.
Mm-hmm. So that's kind of the regulatory approach, which is, I guess the way I look at that is it brings everybody up to the same standard, so that vendor A doesn't get a cost advantage because they're taking a shortcut on what we as a society agree is the basic standard. Then there's the other piece, which is, okay, a new technology comes in, anti-lock brakes, less flammable chemistry. How does that value get translated into an economic incentive for, company X to go commercialize this? Because maybe it's more expensive than a commodity lithium-ion cell. What would you tell, the business guy at that company, how they could sell that more safe product? Are there markets that it could go into that perhaps lithium-ion couldn't go into? Therefore, you could have a higher sales price because then you could add benefit in a certain way. Or is it just a matter of educating the customer? Are there ways of calculating risk premiums? How do you think about that?
So right now, I think if you look at the landscape of where batteries are being installed, anywhere from data centers, commercial occupancies inside electrical rooms, perhaps, to dedicated outdoor energy storage systems. The risks when batteries are installed indoors, both protecting them when they fail as well as the risks to any occupants, most people understand that that's a challenge. So I think that indoor installations is definitely an opportunity area. Equally dense urban settings. Trying really to address those consumer concerns of, is that battery that's being installed next to my house going to risk my health, my house or my property values? So I think that there is a business opportunity there for sure for products that can address those concerns.
And do you think the regulatory codes and the kind of the world that we live in from a code perspective, is it general enough to differentiate between different technologies to basically determine that, okay, this new chemistry, let's postulate there's a new chemistry that has better safety, quote unquote. Can that be translated into the code such that it could then be deployed in places where lithium-ion would not? Or does it require some evolution of the code?
So let's introduce the product standard, the 9540.
Yeah.
So NFPA 855 says how you have to design the system and install it, what kind of training you need to provide. But it also says it has to be 9540 certified. That 9540 certification is what's going to evaluate the hazards of that product. And so it already has off-ramps on it for technologies that don't go into thermal runaway or don't produce flammable gases. There's still a little bit of a gap in there around toxic emissions. And so I think, potentially there could be some proposals to introduce some additional tests to characterize a cell that can go into thermal runaway. Will it produce, cyanide gas, for example, which is potential for some cathode chemistries. So that's one. But I think the other one is the UL 9540 process. It's a really slow moving one. It's a very, very large technical committee. I think it's actually too large to be nimble enough to really move through some of the proposals that are coming through. And that's unfortunate because the manufacturers really rely on that. Anytime there's a change to it, it potentially impacts their product development cycle. And not potentially, it really does. So you really want to have a product standard that's nimble enough to respond to changes in an effective way. And so there's some room for improvement there.
Yeah. What's the current state of the art of responding to large lithium-ion battery fires? And is it different for stationary storage versus, say, an electric vehicle that catches fire?
Yeah.
Have you personally been involved in fires like that? I assume you would have in your firefighting career.
So not electric vehicle, some stationary storage, but they were not listed products. They were more kludged together, MacGyvered projects. So the main priority of the fire service is protecting life and property. And so let's just take a vehicle. If there is a EV on fire, it's a very different strategy if it's parked in a garage underneath the house than in a parking lot with no other cars nearby.
Yeah.
And so for the fire department, one of the things that they're realizing as they go to these fires is it's very challenging to put out. And that's because the fuel is wrapped up with a lot of steel, the battery pack around the whole vehicle. And so when you hear people talk about it's taking 30,000 gallons of water to put a Tesla car fire out, the analogy I put out to people is that's like saying or asking, how much water does it take to put a dumpster fire out when you're spraying water on the outside of the dumpster? Yeah. All of it.
Right.
Because you're not putting it on the trash inside. Right. So because it's really an application challenge, getting the water inside. So what fire departments are realizing is if they do have an exposure risk then they have to be very aggressive. They have to spray water all around to protect the exposure, maybe try and pull the vehicle out, or just spray a ton of water on the vehicle for hours potentially. But we're starting to see more fire departments acknowledge that it might be better to let the fuel consume itself. That is a firefighting tactic in wildland firefighting. We will let it burn to this road or this rock outcropping. Mm-hmm. So it's not that you're giving up. You are letting the fuel do its job. In terms of stationary storage, one of the best practices that's emerging now is that if the system is designed with enough separation to the next enclosure or the next exposure, then the fire department should not have to do anything. Water, like I said earlier, it's a challenging, when you start applying water, now you could be developing additional short circuits. So these vehicles where they were spraying thousands of gallons of water, the fire's all out, it's all calm. 3 hours later, the tow truck comes, they tilt it up to bring up the ramp. Now the water shifts inside and contacts and starts smoking again on top of the flatbed truck. That's happened many times. Driving down the road, start smoking. They've got to drop it off, call the fire department in the next city. So I think the best practice really is to design the system for a no water application and to site it for that and then to train for that. Got it. That makes sense. Great. So I think we're almost at the end of time here. You have any last words for the budding battery safety engineers out there listening to our podcast? Well, to the industry in general. Well, first of all, thank you. I mean, I appreciate the invitation. Yeah. I think that this is an important topic. I do too. And I would say that, for all levels of industry is to, place the safety not only in the design of your product, but to look at it through its whole life cycle. Even think about what the decommissioning and the removal of the product means. That's going to be a challenge for a lot of these systems, especially if there is a failure. That decommissioning can be challenging. So think about the safety throughout the whole life cycle of the product. Be very proactive in your outreach to responders, to the community members. Engage them, listen to them, and really focus on trying to instead of focusing on site density, which seems to be what everyone's moving towards, if you have a little bit lower energy density of a technology, maybe you now have a third dimension. Maybe you can stack systems and have that same site density. So energy density should not be a deterrent to system design. It's really important to understand that impact or that balance of energy density to safety. Well, thanks again, Matt. It's been a pleasure having you on IONS, and we will certainly see you around the sites and the systems as they get deployed. Thanks, Ken.